If the DB changed, your RAG should know automatically. By the end of this video, you will understand a simple, reliable pattern to keep a retrieval-augmented generation system up to date when your database changes. You will be able to reason about why it works and how to build a small, testable pipeline in Python. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Keeping a RAG system fresh is one of those invisible engineering problems. You add or edit rows in a production database, and your vector store or text index stays stale. That leads to wrong answers, and nobody notices until a user complains. CDC RAG sync is a practical pattern that links database change events to incremental index updates, so new or updated content is available quickly without re-indexing everything. At a high level, the idea is familiar. Write changes into an Outbox table inside the same transaction as your data change. Emit a short notification so a worker wakes up fast. The worker claims the Outbox job, reads the committed data, updates the index, and then the new content becomes searchable immediately. It trades a small amount of storage and a simple rule set for low latency correctness. We will build a toy pipeline that follows those exact steps. You will see a live database check, create minimal tables, push a notification, claim and index the job, then run a fast text search over the updated index. None of this requires heavy external tooling, and the code maps clearly to production choices later. This snippet establishes a database connection and verifies PostgreSQL is reachable. The function createEngine builds a SQLAlchemy engine pointing at a local Postgres using the psycopg driver. The withEngine.connect block opens a short-lived connection that automatically cleans up on exit. The call to db.execute with text runs a simple show server version command, and scalar grabs the single cell returned by the query. We store the result in the variable var to ensure we've got a live working connection before building the CDC pipeline. Seeing the printed version confirms your driver, DSN, and server are aligned. Next, we create the tables and seed one document so the pipeline has something to operate on. This example sets up minimal tables for the Outbox pattern and seeds one row. The context manager engine .begin starts a SQLAlchemy transaction, so DDL and the initial insert happen together reliably. The table docs stores original content, while Outbox holds small JSON messages in the column P that describe downstream work. We insert a simple body value, beta x, to keep retrieval deterministic later. The variable n is a tiny confirmation that two core tables were created for this walkthrough. Having a schema and a first document ready lets us focus next on streaming events without ad hoc polling. Now we emit a notification and show how the database can push an event to a worker. This code wires a push path from Outbox to your worker using psycopg. The connection PG subscribes with listen Outbox, so the backend can deliver notifications. Inside oneEngine.begin transaction, we insert a compact JSON message into Outbox and then call PG notify on the same channel, ensuring the event is emitted when the transaction commits. The variable MSG holds the JSON that both persists in Outbox and flows over notify for low latency wakeups. Finally, pg.notifies.get waits up to 2 seconds to receive the event. The printed payload shows an upsert for ID equals 1 and confirms no polling was needed. Next, we consume an Outbox job, read the committed document, and update a small in-memory index. This snippet turns an Outbox entry into a fresh index update. The dictionary index will hold lowercase text keyed by document ID. Using engine begin, we perform a delete returning P to atomically claim one job from Outbox and avoid double processing. The variable P is the JSON payload. We extract its ID into did. A follow-up query reads the current body from docs, and we store a normalized lowercase copy under that ID. This pairing claim then read ensures the index reflects committed data that triggered the event. The printed size confirms a new document was incorporated. Now we run a simple search over that in-memory index and rank candidates by a tiny score. This example queries the freshly updated index and ranks by a tiny score. The variable Q is the search term, and we compute a normalized term frequency by counting occurrences in each body and dividing by the word count. The comprehension produces ID and score pairs, which sorted orders descending by score for a best first result. The variable top holds the winner or a default 0 when the index is empty. Increasing query specificity generally lowers counts and thus scores. Broader terms raise them but reduce selectivity. The printed top ID and score confirm the latest document content is searchable immediately after the Outbox-driven refresh. In a real project, you would map the in-memory dictionary to a vector store or an approximate nearest neighbor index, and the same claim pattern still applies. The worker can be scaled horizontally as long as each Outbox claim is atomic and idempotent. You keep the data source authoritative and the index eventually consistent with low latency. Recap what it is: a database Outbox plus notify pattern that drives incremental index updates for RAG. When to use it: when you need fresh, low-latency searchable content without full reindexes. One caveat: you must design claiming and idempotency carefully to avoid duplicate processing or missed updates. Next step: replace the toy in-memory index with an approximate nearest neighbor index, and run timing and recall checks as you scale the document set. Measure latency and correctness as you increase concurrent workers. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.